I think we'll go ahead here. Thanks everybody for joining. This is the second Innovation Insights Research Seminar in our series this year. So we're excited to have you. We're excited to have Ben Castleman and Kelli Bird here from University of Virginia. They are going to be sharing some research on human versus algorithmic predictions in education. And I know I'm excited to hear what they have to say. So there will be time at the end for Q&A, about 15-20 minutes or so. So keep track of your questions till then. If you have to go or something and you'd like to just drop your question in the chat, or if you have a question and you want to drop it in the chat just so you don't forget it, we can follow up on those at the end. But if you want to put it there until then, that's more than fine. So I'm excited to introduce Ben and Kelli. Ben is an associate professor in economics of education, and Kelli is a research assistant professor, again, both from University of Virginia. So we'll go ahead and let them take it away.
Great. Thank you, Becky. And thanks to all of you for being here. Wish we could be with you in person, but glad to at least have the opportunity to present via Zoom. I'm going to pull up our deck, and then I will start off. And fortunately for everyone, I will hand it over to Kelli as soon as I can so that you can benefit from her much more charismatic presenting skills. As Becky mentioned, we're going to talk about, at high level, work we've done across various projects, exploring the role of algorithms in education with a particular focus in post-secondary education, trying to get under the hood of those applications, and then some nascent field experiments we've conducted to see whether providing algorithmic information to educators, how that affects the way that they in turn support students. So,
hey Ben, sorry,
yeah,
you want to push, can you click the slideshow button? Or yeah.
Thanks, Becky. You'd think I was new to this, but I don't really have any excuse at this point. So just to provide a little bit of context for how Kelli and I started over the last few years to focus a lot on algorithms. Kelli certainly has the technical expertise to engage in this work. I can barely play a data scientist on television, let alone do any actual data science work. And so the foundation is maybe a little bit relevant. Our initial foray into the kind of role in the intersection of technology and education, going back 10, 12 years at this point, was not really anything data science intensive, but something a little bit data science light. And that was a series of projects that we did and that I did with other colleagues, applying text-based nudges to reduce this phenomenon of summer melt, where students have applied to college, they've gotten in, they've applied to financial aid, they've even chosen where to go as at the end of high school, but they failed to enroll anywhere as a result of challenges that arise during the summer months. We developed this interactive text messaging campaign that consisted of like 10 messages over the summer about financial aid, placement tests, tuition bills. Here's an example. And the reason I refer to this as data science light is this wasn't me or our colleagues, sending these messages one at a time on our phone. We had information about students from our district partners, basically their name, their phone number, where they plan to go to college. We pulled down information from college websites about what students had to do over the summer. Those kind of were two separate spreadsheets. We worked with a platform to stitch those together and then sent out to hundreds and then thousands of students these highly personalized text messages. Over several experiments, both on summer melt, you can see in the middle, we did very similar projects focused on FAFSA completion, FAFSA renewal. Through field experiments, we found that in early and fairly local texting campaigns, that this approach could lead to fairly sizable improvements in both college enrollment and college persistence, especially for an intervention that cost only a couple or a few dollars per student. Please do pay attention to the y-axis. These are all significant estimates, but you can see they are somewhat imprecisely estimated. And so that may be relevant in a moment. This is also the early 2000s. The texts were from nonprofits or school districts with whom students had a direct relationship. As you saw a moment ago, the content was personalized, and students could write back and engage with an advisor if they had questions. This kind of is one of this types of research where perhaps it was something about right time, right place, where there's kind of growing focus on expanding access to post-secondary education. Certainly that was a focus of President Obama's second term, focus of Mrs. Obama. And so as the results from these experiments were coming out, we observed and were able to participate in fairly broad and rapid adoption. So there were statewide texting campaigns in West Virginia, in Texas, in Hawaii, in Minnesota, in Delaware. And Mrs. Obama notably championed, as part of her broader Reach Higher initiative, her own text campaign, which was broadly based on some of what we had done. We had the opportunity for some of these to participate in very, very large-scale field experiments. And then we also designed some of our own very large field experiments at the level of an entire state or working with national nonprofits, where the samples are in the hundreds of thousands. And this is what we found, whether it was working with the common application. This set of texts all focused, mostly focused on FAFSA completion or college going, whether it was working with a large state, the College Board, the U.S. Army, the kind of nationally representative sample through the Institute for Education Sciences. No effect of these text campaigns when we brought them to scale. You can see the y-axis is much, much smaller, so we have much greater precision. We can, for most of these, rule out that the texts had anything larger than a kind of 2 percentage point increase in enrollment. And there are some important contextual differences, right? This is the mid to latter 2010s, where texting was more common. Perhaps it was an information saturation problem. The texts were coming from national organizations or state agencies with whom students had, at best, a distal relationship, and in many cases, no real relationship to speak of. By virtue of texting hundreds of thousands of individuals, the content tended to be more uniform. Because of resource constraints and the challenges of just hiring sufficient advisors, in many cases, students were receiving just one-way content. And again, we, across numerous replications, found that these texts, which had been quite effective at a local level, especially relative to the cost, were not effective at a broader level. That's the kind of foundational context that arose, I think, around the same time that there started to be increasing application of data science and associated economic research of data science in other sectors, criminal justice, healthcare, that got us increasingly curious about the potential to bring to bear data science methods for prediction and recommendation into the post-secondary sector, with a kind of similar North Star focus on improving student outcomes. So, much of our mid-2010s, latter half of 2010s focus was on why these nudges didn't work at scale, and how we might, in turn, shift our strategy. It could be, for instance, that especially when we're messaging hundreds of thousands of individuals, we were just targeting the wrong students, or we were targeting the wrong margin of students. And this got us interested in data science methods for prediction, where perhaps we could identify students most in need of support and focus our texting or our other interventions on those. We also, I think, were fairly persuaded that information alone, absent access to kind of individual support from a knowledgeable advisor or educator, might be ineffective. And we started to wonder whether leveraging recommendation engines, the kinds that Netflix uses to tell us what movies to watch, or Spotify uses to tell us what music to listen to, could increase the efficiency of human supports at scale. If we could give an advisor, for instance, a set of course pathways or college pathways that were really tailored to a student, perhaps that could let advisors be much more efficient in the time that they engage with students and therefore have larger caseloads, serve more students. And we also, of course, wondered whether our information in these nudges was too generic, which in a similar way led us to be interested in the potential to provide students with much more tailored educational or even career pathways on the idea that that information might be much more salient to the student and in turn lead to higher rates of engagement. So, as we start to think about this, what we were observing among colleges and universities, both those that we engage with directly and what we read about, was what seemed to be a fairly simple but yet common theory of action for data science applications, as we started to learn more about this and investigate our own potential applications. There was this broad goal we saw across dozens or hundreds or probably now thousands of colleges and universities to identify students at risk of academic struggle or at risk of stopping out of a university before it was too late, before they were already off track. This concept of early alerts came up in lots of conversations with college administrators. This probably peaked during COVID, where 80% of colleges and universities were using predictive analytics in some fashion to identify students who might not be successful, who had, might be at risk of not re-enrolling. And this was costing hundreds of millions of dollars per year, probably more at the peak of COVID. Following this theory of action forward, I think the general idea was, well, if we can identify students at risk of support, we can in turn provide those students who are flagged as at risk with additional supports. And if we do that, those students will be more likely to succeed. As as people who do primarily experimental evaluations and are very focused in causal impact evaluations, one of the other things that struck Kelli and I struck some of our colleagues, was that the pace at which predictive analytics and early alerts were being applied by colleges and universities seemed to greatly outstrip the evidence base on whether providing predictions to instructors or to advisors or reaching out to students themselves was actually leading to improved student outcomes. So in the kind of broad spirit of wanting to understand whether the application of data science methods, prediction and recommendation algorithms in post-secondary education works, our focus has been on two broad areas. One, trying to get under the hood of data science applications in education. And then the second, as I mentioned earlier, actually trying to put data science methods to work to provide students with more tailored recommendations or to connect students to have identify for instructors students who early in the term might struggle to succeed absent additional support. I'm going to briefly talk through the first couple bullets here, which I'll describe in a moment, and this question of algorithmic bias and our field experiments testing data science applications. Kelli will pick up and run with. So the two questions initially that we started with, one was this kind of foundational question of, if all of these colleges and universities are assigning these risk ratings to students, how stable is the concept of student risk? Part of what motivated us to want to look into this was our own observation that much of the prediction models in post-secondary education seem to be developed and implemented by private sector companies that treated their modeling as proprietary and therefore were quite opaque about what modeling methods they were using, what data was feeding into those methods, how that data was structured. So in one paper, we used data from the Virginia Community College system, and we systematically tested different prediction methods. So OLS, logistic regression, on up to random forest and neural networks but also systematically varied the data that we incorporated and the structure of the data to see how consistent model performance was across specification. But again, in our mind, more fundamentally, how stable the concept of student risk is. If Kelli, let's say better yet, me, if I'm kind of predicted as being very likely to drop out prior to earning a degree in one model, as educators, researchers, policymakers, we'd probably have more faith in this general concept of prediction if my prediction of being highly at risk of dropping out is more or less the same, regardless of modeling method used, and hopefully fairly robust to different data specifications. So that's one question that we're going to look at. The other question that we felt was pretty foundational to investigate is how algorithms compare in their accuracy of predicting an outcome than humans. Humans, on the one hand, may be able to factor in more contextual information about students, but we know from a lot of work that humans bring their own implicit biases. And so in another paper, which again, I'll just highlight very briefly, we trained an algorithm to predict whether students in a national college advising program would enroll at a selective college or university. And then we had a group of advisors who had worked with those students all year generate the same prediction. Would the students in their caseload enroll in a selective college or university? So let me just kind of briefly talk through those, and then I'll turn it through Kelli to talk through these other items. So to the concept of how stable student risk is, this is on the surface a complex figure perhaps, but I'm just going to focus on the bottom row. Each of the columns here is comparing whether a student predicted to be in the lowest probability of completion, the bottom decile of completion, by one modeling method is also predicted to be in the bottom decile of completion with a paired prediction method. So I've circled a few examples for here to us to look at. If we compare an OLS method for prediction to a logit method for prediction, holding data constant and data structure constant, the overlap is quite high. 86% of students in the bottom decile in an OLS model are also in the bottom decile in a logit model. But what you can see is if you scan across the bottom row of this table, stability is much less consistent across other methods. So if we compare the students who are in the bottom decile of predicted completion from a logit model, only 53% of them are when we generate the same prediction, again, holding constant data and data structure in a random forest model. When we compare a random forest prediction to a recurrent neural network, again, it's only about 50% overlap. So this was a bit of a red flag or kind of cautionary note for us on the use of data science methods to predict students at risk of completion, given that the concept of student risk seems relatively fluid, depending on the modeling method used, and particularly given how opaque it remains on what models are being used at many colleges. Part of this is the fact that roughly 2/3 of prediction models at colleges and universities remain kind of homegrown and therefore fairly idiosyncratic and not well documented. But the other 1/3 or so are proprietary. There's not a lot of open source kind of broadly used prediction models where one can really interrogate these questions. And we see this similarly if we're kind of using the reference as the third decile in the risk distribution or the fifth decile in the risk distribution. So again, the concept of student risk seems perhaps more fluid than an administrator or an educator or a researcher would want it to be. The other thing that was striking to us, now turning to this question of how algorithms compare to humans, on the kind of, this is comparing whether on the x-axis, an advisor predicts a student as being very likely to enroll in a selective college or university, with 10 being very likely, 2 on the y-axis, how an algorithm predicts that same student to have a likelihood of enrolling at a selective college or university. These are positively correlated. That's good, right? But it's also the case that if you look at students who advisors predict to be super, super likely to enroll at a selective college or university, there's a decent mass of those students who the algorithm thinks are fairly unlikely to enroll at a selective college or university, and the vice versa is true. What we find comparing advisor and algorithmic predictions to actual student enrollment is that about both are correct for about 50% of students. For just under 20%, the advisor is correct, but the algorithm is not. And then for another 16 or so percent, the algorithm is correct, but the advisor is not. This is providing, just a little brief context, the algorithm with information on like students' SAT scores and their AP taking and their demographic information and where they applied to college. The advisors are able to factor all of that in, plus all of their, qualitative or contextual information on their interaction with students. The advisors also were engaging with students, for some students substantially throughout student years, so they knew where students had been accepted to college, what financial aid they had gotten, for context. As we dug into this a little more, one of the striking patterns was that overall, it is the case that humans tend to be modestly more accurate in their prediction of whether students will enroll at a selective college or university, but that accuracy is entirely concentrated in students with whom advisors had quite a high volume of interaction. So if students are in the kind of top 2 quintiles of interaction frequency, humans are much more accurate. But for the majority of the distribution, the bottom 3 quintiles, the algorithm is actually more accurate, even though humans had kind of more information to go on because the humans had actually interacted with the students. So on the one hand, from our kind of descriptive investigations at this point, we had seen like maybe we should worry a bit about the fluidity of risk as a concept. On the other hand, especially if we think about applications at scale, where it may be challenging for humans to interact with students with sufficient frequency, maybe algorithms are actually comparatively fairly decent at identifying the student outcome, and maybe therefore we want to leverage them further. So with that, I'm going to turn it over to Kelli to talk about our investigation of algorithmic bias, and then from there, our application of data science methods in the context of a couple field experiments. And Kelli, just shout when you want me to advance.
Sure, will do. Thanks, Ben. So moving on to talking about algorithmic bias. So many people have concerns about potential racial bias in algorithms, and rightfully so. There's a growing body of research that shows meaningful racial bias in other predictive analytic applications, like in criminal justice or in healthcare settings. So we decided to take 2 of our prediction models, both within the context of the Virginia Community College system, but one predicting successful course completion and the other predicting successful certificate or degree completion. And we decided to define bias using this definition of calibration bias, which I'll describe. But there's just to note that there are a lot of different definitions of algorithmic bias, and there's no real consensus yet on which is the best to use in which cases. So you can see this figure on the x-axis, it plots the percentile of the raw predicted score. So an algorithm will shoot out roughly a student's probability from 0 to 100% of completing the course. And on the y-axis, we have the percent of students who actually, as observed in the historical data, completed the course based on where they are within the distribution of their predicted raw score. And we can see the blue plot is for the white students, the green plot is for the black students. So conditional on a predicted score, the white students actually have a higher success rate than the black students. Next slide, please. So, so why would this calibration bias be a problem? So suppose that we set a threshold such that students in the bottom 3 deciles would be flagged as at risk and targeted to receive additional supports. So at that margin with this calibration bias, relatively more white students would receive the additional supports, even though they would have succeeded at baseline, and relatively more Black students would not be targeted to receive additional supports who would not have succeeded. So we quantify this amount of bias by simulating results where the success rate at a particular cutoff would be equal to white and Black students. So moving those two curves together, and seeing how many additional Black students would be targeted for the additional resources in this unbiased simulation. And so we do this for a variety of different risk thresholds, but for this example of using the bottom 3 deciles, we find that in the unbiased simulation, 15% more Black students would be flagged as at risk and therefore receive the additional supports. Next slide, please. So to highlight a few other findings from this study, we find that the pattern of bias varies substantially between the algorithm predicting the successful course completion, which is the plot on the top left, versus the algorithm predicting graduation, which is on the bottom left. And this is despite that the models are otherwise really similar. A lot of the similar predictors, it's all based on the same student data within the same context built by the same researchers. So it's surprising to see these very stark patterns in the differences in the algorithmic bias across the distribution of predicted scores. And then we also tested how making the models more attuned to race would affect the bias by either including racial predictors directly in the model or by estimating race-specific models. And we found that it decreased the amount of bias in the course completion model, but increased the amount of bias in the degree completion model. Again, really highlighting the context-specific nature of bias in these models. And then we also, tried to dig in to see what was causing the racial bias in the models. We don't have, a solid answer. We did rule some things out, though. We tested whether the bias was due to underrepresentation of Black students in the historical data, but we did not find evidence to support that. Also, we didn't find evidence to support that it was due to differential sorting. So maybe, if Black students were taking a different types of courses or programs of studies, and that would be explain the bias, but that didn't either. Next slide, please. So to summarize what we've learned in the recent work that gets aimed at getting under the hood of the data science applications, we found that the concept of student risk may vary significantly across many common prediction models, that humans and algorithms have similar accuracy in their predictions, except when the humans interact with the students in a pretty significant way, and that the calibration bias can, within the models that we tested, can lead to fewer Black students at the margin of success receiving additional supports. But we also highlighted that the amount of bias is really highly context specific. But through this line of work, we've gotten under the hood of the data science applications, but it doesn't really answer the question as far as whether the use of these algorithms can improve student outcomes. Still very much ambiguous. And so, our goal in recent years has been to test that question more explicitly using some randomized control trials and pilots with our community college partners, but not to bury the lead, but we have run into some challenges in doing so, which I'll talk about as well. Okay, so the first pilot that we designed with our partners at Virginia Community College was to use an algorithm to generate personalized course recommendations for community college transfer students to be delivered through an intrusive advising approach. So coupling the human resources with the algorithm generated recommendations. Next slide, please. The overarching goal of the pilot was to improve the transfer and eventual four-year degree attainment outcomes for community college students. So even though most community college students plan to transfer to a four-year, only about 1 in 4 actually do so. And some of our hypotheses for why this is that, you know, this could be due to the complexities of the transfer pathways to four-year institutions. In Virginia and in many other states, there are articulation agreements between community college and four-year colleges, but at least for our research team, you know, we had to read them 5 times over to even feel like we had a sense of what was going on. They were very dense and legal documents. And then even among those students who do successfully transfer, you know, at the community college, many of them lose credits, which extends their time toward their degree. Next slide. So our pilot solution was we worked with a community college to pilot a intervention that involved delivering these personalized course recommendations generated by an algorithm, and to have that delivery be done through the advisor. So students, and this was a randomized control trial, so the treated students were contacted by the college to review the algorithmic recommendations with their advisor. And we designed the algorithm specifically with input from our community college partners, you know, to achieve 3 goals. One was to get the student to graduate from the community college faster. And so we only recommended courses that would count towards their community college degree requirements. The second was that we gave preference to courses that our grade prediction model predicted that the student would earn either an A or a B/N. And then also we maximized the number of credits that would transfer course for course to a 4-year institution. Next slide. So this is an illustrative example of what a student would see with their advisor. You know, we wanted to make the community college degree requirements and transferability requirements clear to the student, and you know, where possible, we also customized the recommendations based on intended 4-year school and their intended major there as well, as you can see. So we had high hopes for our course recommendations when we compared our recommendations to the courses students and, you know, the historical sample actually took. We found that if they had taken our recommended courses instead, that that would have increased the number of credits that they earned toward their degree by 2.7 credits per term, and would have increased the number of credits transferable directly to an institution like UVA by 2.9 credits. Next slide. But we did encounter several significant challenges with the project. The first, and this was a little surprising and frustrating, was the complexity of coding the community college and the 4-year degree requirements. So even in working with one community college, they didn't have a reliable automated way of degree auditing. So telling us, you know, the requirements a student had already satisfied and which ones they still had to satisfy and which courses could satisfy the remaining requirements. So we had to figure out how to code those on our own. It was surprising how much time and effort that took. And then the second challenge was you know, building an algorithm that required actually a lot of subjective decision making. So we had to specifically weight how much the predicted grade should matter for the recommendations versus the course transferability. And then lastly, after the pilot was implemented, we saw that the advisors revealed views of the algorithm were maybe not quite what we hoped. Next slide. So during the pilot, we found a significant disconnect between the algorithm and the human decisions. So when the students and the advisors met together, the advisors recorded which courses the students told them they would plan to enroll in. And on average, students chose only about 40% of courses from the recommended list. So that could be driven by, student preferences or schedule constraints. But when the advisors went in for the non-responsive students and edited the courses that they were going to email the students that they hadn't met with, the advisors changed about a third of the courses before sending them to the students. And so we compared the list of the original recommendations to the ones that advisors actually sent, and the advisor put less value on predicted grades and instead chose the best courses, assuming the student would succeed. So the courses that advisors chose were more likely to transfer course for course, for example. And it would be really interesting to test, do a race between the human only versus the algorithm only versus the human plus algorithm choices, but we only have one of those. So we still, unfortunately, don't know which is better. Next slide. So the second pilot, which is currently in the field, is using early term predictions to target student success groups. And so Ben already did a great job at the beginning of the presentation motivating the problem and the potential solution using predictive analytics. So the specifics to this pilot was, again, we worked with a community college partner to provide instructors with a list of at-risk students that we would deliver during the first quarter of the term. And for half of the instructors who were randomly assigned to receive the model predictions, we also wanted to provide them with additional student success supports. So this included things like additional dedicated course section tutors and a college navigator that could work with the instructors and other existing supports to help support the students. And we also, developed some messaging protocols to be intentional on, how the instructors and then the navigator were communicating with students. As you can imagine, not well thought out communications about students being at risk could backfire. Next slide. But again, we hit several challenges with this pilot, and it led to us not being able to run it as planned. So the biggest challenge was that the prediction model relied heavily on data from the learning management system Canvas, which is click level data describing student behaviors within Canvas. And this data is necessary for this pilot because we were targeting gateway courses, so courses that first time students often took. And when we have first time students, especially in community college, we don't have very much information about them. So incorporating this clickstream data predictors are really important to getting high enough accuracy. But the raw data is super cumbersome, requires complex transformation, and despite significant investment in both data storage and computing power, we were unable to get a working version of a database that would fit our project's needs without having to make even larger and longer term investments in database management. So we pivoted to using kind of like a human algorithm approach, in that we have a great partner at the community college who is working with the college navigator that we hired and the instructors to identify at-risk students and encourage the use of the additional supports that we were already planning on providing. So I'm going to wrap up because I know that Ben and I would love to hear from you all. So I'll just conclude, summarize the overarching lessons that we've learned from our work thus far. First is that the best choice of algorithm is likely highly context specific. So even though overall accuracy may be similar across models, there are several subtle changes in which students are on which side of each threshold that can greatly affect who's considered to be at risk. And as been mentioned, most algorithmic applications in education are pretty opaque. So it's really not clear what methods are most frequently being used in this area. And then the second overarching lesson is that it's important to consider how to balance, the new potential role of algorithms with the ongoing role that humans have in student success. So one example is thinking about what level human buy-in is necessary. So in our transfer pilot, we had really wanted advisor buy-in, which wasn't fully achieved. So, could we have restructured it so that we sent the recommendations directly to the students? There are pros and cons with both approaches. And then we also demonstrated the racial bias in models, but it's important to consider that humans, of course, also have bias, whether it's explicit or more likely implicit bias. And when it comes down to building algorithms, even something that seems like from a high level it would be an objective process, it really does require a lot of human subjective decisions about how to prioritize different factors in achieving student outcomes. So finally, while we see a lot of promise in incorporating some carefully designed data science applications to improve student outcomes, there's still significant technological barriers to do so, and particularly in a fashion that would be highly customized and contextual that we think would be necessary for the long-term success of those applications. That is all I have. Happy to open it up to questions, however would be best.
Yeah, thanks so much. I'll just invite folks to use the little reaction button to raise your hand, and we'll try going from there. So if you had one and would like to share, please go ahead and do so. I've got some in my back pocket if we're starting out kind of like a quiet bunch, but
I've got one. Have you talked to the advisors about what they were selecting for? If they were removing courses and not looking at grades, what were the characteristics that they were opting into?
Did we lose Kelly?
I think we just lost her. Shoot.
Okay. It's a great question, Kate. Kelly is closer to this analysis, but a trade-off would be something like it would fulfill a kind of general education equivalency at UVA. And so to Kelly's point, conditional on the student earning a decent grade in the course, maybe on the margin, the course would have greater equivalency at a university. That would be one example. Another example that I recalled in the pilot is that advisors have kind of heuristics. So they think a student should take a balanced load, a math, a science, a humanities, and an algorithm may not suggest that, right? If an algorithm is trying to maximize success and a student, based on what we can observe about them, is most likely to be successful in 3 math courses, that's what the algorithm is going to put forward. I'm not suggesting the algorithm is absolutely right or that an advisor set of heuristics is inherently wrong. It just highlights the potential difference. And I mean, Kelli alluded to this. I think this question of trying to understand and investigate more thoroughly the kind of relative efficacy of the kinds of recommendations humans make versus what an algorithm would make strikes me as very important, because I think this work is happening. It just may not be happening. Like the application of algorithms and the use of algorithms for things like course recommendations is happening. The question is it being rigorously evaluated and rigorously compared to human recommendations?
That's great. Thank you.
Kelli, I appreciate you ducking out just as the question came up that I didn't know how to answer. Thank you very much.
I'm sorry, I didn't even hear the question. My computer pooped out on me. Sorry about that.
Welcome back. I did my best.
Okay.
That's okay. I'm gonna follow up with a related question around this advising project. And I'm wondering, like, how were the advisors kind of involved, if at all, in like the project to develop the algorithm from the beginning, right? Like humans never use anything the way it's like kind of intended to be used, right? But like, how closely were they involved in the project, truly, if at all? You know.
Maybe I'll take a first stab, because I think it's a fantastic question. You know, one could imagine a world in which we as outside researchers worked with, like, you know, senior leadership at the college to design this thing, and it just like plopped it in the laps of the advisors. In that implementation model, one could imagine high rates of disagreement, right? Because for all the reasons we know, advisors are like, who are these people? I don't trust them. I don't know them. Therefore, I really don't trust the algorithm. Our approach is kind of the opposite of that. Across all of our projects, we are very collaborative and kind of take a co-design approach. So not the sense that like we weren't working side by side with the advisors and training the algorithm, but we were engaging with the advising team a lot, describing the algorithm structure, getting their feedback, refining it, talking about how the project would be implemented. So in this case, the advisors, it was a team of 6 people or so, had very strong awareness before the experiment started of what we were doing. They had input into, at least at high level or at an intuitive level, what the algorithm would prioritize. They had seen what the output would look like. And yet as Kelli shared, when it came down to the, you know, in the implementation semester, actually seeing lists of recommended courses for students, either the advisors on their own said, nah, for about a third of these courses, we think it should be differently. Kelli, when you were off, I shared the example of the kind of heuristics advisors use. Well, students need to have a balanced set of courses, a math, a science, and an algorithm, depending on the student's background, might say, no, 3 math courses are great for this student. You know, so the advisors would see that discrepancy between an algorithmic set of recommendations and their own set of heuristics and make changes. We also don't know, in the context of advisor-student interactions, how much of the pressure to make changes came from the students themselves. That's where about 40% of what students actually registered for differed from the recommendations. Some of that might have been the advisor, but some of it might have been the students who have their own heuristics, right? Like, I don't care that this algorithm is saying I should do well in these 3 math courses. I don't want to take 3 math courses, or I don't want to take this particular business administration course because one of my peers told me this other course is better. So that it's this very interesting interplay between you know, decision-making and behavioral biases and algorithmic recommendations that I think we have just scratched the very tip of the surface of. I think this is an area that, you know, would benefit from a lot more work.
Yeah. Decision making in higher ed is such an interesting space for sure. Are there any questions from the crowd? It's your time to shine. got a quiet bunch today. Okay, I'm gonna ask you one more. And this kind of goes back to the first project that you were presenting on, like, is the concept of risk stable from model to model? And I may be misinterpreting, but I was sort of also assuming that your question was being asked, like, is the concept of risk stable from university to university or from environment to environment? And I'm not sure if that's correct. You can correct me if I'm wrong, but or where I'm wrong. But I kind of wondered about that idea of students being similarly at risk from one spot to another. Like the same student at one university may be truly at risk of academic struggle, but that same student with a different learning environment, a different university might be, not as much at risk based on whatever the supports are or whatever, their choices are there. So I didn't quite understand, or I wanted to know more about, like, how does that idea kind of layer on top of your question about the stability of risk?
Kelli, do you want to take a first stab?
Sure. Yeah. So in our specific project, we focused on just the exact same group of students, all at the same colleges that they actually enrolled in, and comparing the stability of risk across different prediction models. So using the same data, exact same context, and just looking at, what if I wanted to do OLS versus logistic versus recurrent neural network. But the question that you have is a great one, and unfortunately, I think probably much more complicated to answer, because you would need, I'm just thinking through, like, the technical bits of course, the different data that you would need, the different models of that are university or college specific. So I think that would be a very interesting thing to look into. My assumption is that the risk stability would be even more variable. What particularly given the different types of information that colleges collect about their students, it would be pretty difficult to get that to match with across data sources. So sorry, Ben, did you have anything to add?
No, yeah, I mean, my strong assumption is that any student, potential for success is to some extent context dependent, right? It's why we don't, it's hard to know, for instance, the returns to attending, Harvard versus public flagship versus community college, because there's so much sorting of student background and ability across those institutions. The thought experiment, like if you could take a student and put them in any one of those institutions, maybe a really kind of academically capable student would be successful in any, right? These are difficult questions to really sort out. And so I do think context matters, but as Kelli said, we were really trying to take on the perspective of like a university leader who's saying, I've scarce resources to allocate. And if I want to focus on the most at-risk students, or I want to focus on like students at moderate risk, because maybe those are ones who are kind of marginal to my intervention. Is there some group of students who are always going to come up as moderately at risk, regardless of what modeling approach this private vendor uses? And the answer is no. Like, it's going to be a different group of students who are identified as moderate risk within an institution, depending on the method that a vendor uses. That was, I think, one of the key insight we were trying to highlight there. But your point is very well taken. A given student who's moderately risk in one institution may be better positioned for success in a different institution because of differences in instruction or advising supports and so on.
All right, well, we'll put a pin in it there. Thank you so much. We really appreciate your time, and your efforts to understand how to better support students. For those of you who are remaining, you might take a quick look. Oh, it didn't come up. There's another seminar up next month, first Monday of the next month as well. So you can find it on our website, or I don't know, the screen sharing is not going so well right now, but yeah, you'll be able to find, there it is. There it is. So William Bork from Michigan State's gonna chat with us next month. So look forward to seeing you all then. Have a good rest of your Monday, everybody, and thanks again, Ben and Kelly.
Bye, everyone.
Thanks so
Thanks.
much.
Thank you. Bye-bye.